In the previous chapter, we already covered about the function of several variables, and we were discussing about the limit and the partial derivatives. So in this chapter, it's going to be about integration of the function of two variables. And the thing that we're going to study is going to be the double integral. And the double integral is going to it's going to come in two ways. The first way is going to be the double integral over the rectangle. And the second one is going to be the double integral over the general region. So the first one is going to be just the basic one. It's going to be like in calculus one that when you like to find the area under the curve. If you recall the calculus one that we have the graph of the function f. So we have y equal to fx, and you have this graph over the interval ab, and you want to find the area under this curve. Okay, so if you like to find the area under this curve, the thing that you can do is going to be you can find this area will be integral from a to b of fx dx. And this is what we learned in calculus 1. Okay, so when we like to find the area, and if you recall, when we like to find the area, we gonna use the thing that called the Riemann sum. When you have some kind of a bar like this one, okay, so you have a bar like this, and you're gonna subdivide this thing into smaller bar, and you sum all of the bar up, and the thing that you're gonna get is gonna turn out to be the thing that called the Riemann sum. So we can think about that thing as one-dimensional. So you just have this area, and you're gonna have the bar like this one, and you're gonna sum all of the bar all together, and you would get the total area. However, if you have calculus 2, you're going to begin with your surface z equal to fxy up here, and you see that you're going to have the domain of your fxy, which is the rectangle D down here. And if you can divide the rectangle D into like a table or into a grid of table like this one, so you see that you're gonna get a grid table like this, and you'll be able to compute. Okay, so you'll be able to compute the volume of each bar. So you see that you have the rectangle down here, and you're gonna get a bar like this one. So when you compute, you're gonna get the volume of this bar. So it's gonna be width times length times height, and you be able to get the volume. And if you sum this volume up, okay, so if you sum this volume up into dimensional, so you see that you have to sum with respect to x, and you have to sum with respect to x here, and you're gonna sum with respect to y here. So you see that it's gonna be uh, the sum that look like the Riemann sum that we had last semester. However, it's turned out to be two-dimensional, not one-dimensional, like the area that we had in calculus 1. So this one will be written in terms of the double integral instead. So this one, instead of one integral, is going to be two integral. And this guy turned out to call the double integral by, you see that we have the side of the integral side turned out to be double. Okay. And this one will give you the volume of the solid under the surface z equal to fxy over the region rectangle D, and it's going to be the product between the cross interval AB and CD. This notation will represent the x and y. Okay, so the first guy will be the boundary for x and the second term will be the boundary for y. And when you like to compute the double integral, it's going to be kind of the same idea of the partial derivative. You're going to transform the double integral over d into, you see that you are having x and y. Okay, so let me use some color here. So you have x from a to b. So this one will be my x, and you have y from c to d, so that will be my y. So you see that we're gonna have x and y correspondingly. So you see it's gonna be integral from a to b of the function f(x,y), and you're gonna integrate with respect to x, and that's gonna cover the variable x. And the second one will be integral from c to d, and you see with respect to y, and it's gonna cover the variable y. And you see that it looks like you putting parentheses corresponding to the color. So you have a to b, so you're going to have dx for integration, and you have c to d, you're going to have dy for the variable of the integration. Similarly, you can interchange the order or you can switch the order in this case. So if you like to find integral c to the inside, so I'm going to use my yellow color. So I have c to the inside. So I just switch dy to the inside. And I have integral a to b outside. So I have dx outside. So this one will give you two ways to like compute the value of the double integral. Okay, so you see that the color must be matched. Okay, the pink will be with the pink and the yellow will be with the yellow, and it's gonna like parentheses. You cannot have integral from a to b dy. So if you see something like this, it must be wrong. Okay, so if you have the color not match like this one, the yellow turn out to correspond with the pink one like this one is turned out to be wrong. Okay, so the pink one correspond with the pink one, the yellow one corresponding with the yellow one. Okay. And one thing that we're gonna have to compute turn out to be the integration formula. So for the integration formula, we're gonna just have the basic one, like when you like to integrate the power function x to the k dx. So for this one, it's going to be just x to the k plus 1 over k plus 1 plus constant c. Okay, when you have k not equal to -1, and you have integrate 1 over x dx, it's going to be log absolute x plus c. Okay, so that is going to be two formula for power function. And we still have the basic one like integrate e to the x dx equal to e to the x plus c, and integrate psi x dx equal to negative cos x plus c, and you have integrate cos x dx will be just psi x plus c. So we have this kind of formula in order to integrate the function that we're going to see in calculus 2. Okay. By the way, if you like to integrate constant, okay, so we also need to integrate constant. When we like to integrate constant dx, okay, so when we like to integrate constant dx, so this guy turned out to be constant. Okay, so it's going to be constant multiplied with x plus c. Okay, so it's going to be constant multiplied with x plus c. Let me make this guy a little bit clearer. Okay, and if you have constant multiple, so if you have c f x dx, so for this one you have constant multiple, so you're gonna just ignore the constant and you just integrate the function. This one will be the thing that we used to do in calculus 1. However, what will be different from calculus 1 turned out to be when you like to integrate. For calculus 1, it's going to be the function, only one variable, x. Here is going to be the function in two variables. So you see that it's going to turn out to be x and y, and it's going to be give you in terms of uh, the domain D, which is the rectangle 1, 2, and negative 3, 0. Let me sketch this guy for you a little bit. So you know that this one is gonna give you x between 1 and 2 and y between negative 3 and 0. So for this one, you graph this guy as y negative 3, 0 and y is 1, 2. So you see you have negative 3, 0. Okay, so for y, and you have x between 1 to 2. Yeah, you have x between 1 to 2. So you have x between 1 to 2. Yeah, so it's going to be come this part, and you have y between negative 3 to 0. So it's going to be this color. Okay, so the rectangle that you are having turned out to be this rectangle. So it's gonna be this guy, this guy, this guy, and this guy. Okay, so this one will give you this rectangle. Okay, so it's gonna be one, two. Okay, so it's gonna be this rectangle D that you have here. Yeah, so it's gonna be rectangle D. And you see that you're gonna have y and you're gonna have x between 1, 2 and y between negative 3 to 0. So this guy can be written or can be transformed in terms of the double integral of x y squared dx dy, and you have the x between 1 to 2, so you're gonna put 1 to 2 here, and you have dy turned out to be negative 3 to 0, so it's going to be negative 3 to 0 for the yellow color, and you have for 1 to 2 is going to be the purple one. Okay, so this one is how we set up this double integral. And I told you that we'd be able to set this thing up in another way, so you can have y inside. So you have double integral xy squared, and you have dy dx, and you have y from negative 3 to 0, and you have x from 1 to 2. So you see that you have the yellow one inside and you have the purple one outside. Okay, so this one is two way to set up this double integral, and we gonna compute for value. And the way that we're gonna compute for value will be we gonna evaluate the inside parentheses first. So the thing that we're gonna do is gonna be we're gonna try to evaluate the inside parentheses. So this guy is the term that we have for the inside parentheses. So you basically gonna integrate this term. So you're gonna integrate this xy squared dx, and you have y squared here turned out to be constant. Okay, so y square here turn out to be constant. So you're gonna have y square and you integrate 1 to 2 of x dx. So this is what you have for the constant. You allow to just move it outside by constant multiple. Okay, so this is what we did for constant multiple. So you see that you can just pull out the constant in front of the integral, and you're gonna basically integral from 1 to 2 of x dx. So this one will be x squared over 2 from 1 to 2, and y gonna copy down. Okay, and you see that it's going to be y squared, and you have 2 squared over 2 minus 1 squared over 2. Okay, so this one will be just the term that you have here. And then this one done. Okay, so for the pink one, so we're gonna continue pulling down, integrate -3 to 0, and you have dy. Okay, so you begin pulling down -3 to 0, and you pulling y down. So you gonna just combine these two guys. So this one is gonna be 2 minus 1 half. So it's gonna become 3 half. So this guy is 3 half. So this double integral will be integral from -3 to 0 of 3 half. Okay, so I use the pink one, so it's going to be 3 half y squared, and I have dy, and now I can just integrate y squared. I integrate y squared, so I get 3 half y to the third over 3, and this one cancel, so it's going to be -3 to 0. So you would just plug in. Okay, so you would just plug in y equal to 0, subtract by y equal to 3, -3 to the third over 2. So for this one will be 27 over 2. Okay, so this one will be the whole calculation for the first double integral that we transform. Okay, so we have the constant in terms of y squared. The second one that we gonna compute gonna be if you have this one inside. So you gonna integrate xy squared by dy. So for this one, you're gonna have x is a constant, and you're gonna just compute the inside integral as before. So we're gonna obtain, okay, so we're gonna obtain this one. Okay, so for this one, you're gonna have x, and you have integrate -3 to 0 y squared dy. Okay, so you have xy squared dy like this, and you gonna just integrate y squared, so you get y to the third over 3 from -3 to 0, and you would just copy x down. Okay, so this one is going to be our x. Okay, so you just copy this guy down, and you're gonna just plug in. You have x, and you have 0 to the third over 3 minus -3 to the third over 3 as well. Okay, so this one will be 27 over 3, so it would be 9. So this one will be 9x totally. Okay, so it's going to be 9x totally. And you're gonna just bring down the outside integral. So you're gonna just bring down integrate Okay, so you're gonna bring down integrate. Let me shoot like this. So I'm gonna bring this one down. So it's gonna be integrate from 1 to 2, and you have dx. Okay, so for this one, it's gonna be integral from 1 to 2, and you have integral from 1 to 2 of dx. So this guy will be 9x square over 2 from 1 to 2. So it's going to be 9, 2 square over 2, 1 square over 2. So it's going to be what? It's going to be 2 minus 1 half. So it's going to be 9 times 3 over 2. So it's going to be 27 over 2. Okay. So you see that we'll be able to compute this double integral in two different ways. Okay, so you can have dx inside and dx outside. Okay, so the first case is dx inside, and the second case you have dx outside. And at the end, you obtain just the final answer, the same final answer, 27 over 2. Okay. So basically, for when we like to compute the double integral, you don't have to do both of them. You just pick one. Okay. So let me remark for you a little bit here that we do not need to compute. Okay, so we don't need to compute both of them for value. Okay, so just pick one. Okay, so you basically just pick one integral, and if you compute it correctly, you're gonna obtain the same solution or same final answer anyway. Okay, so that will be the thing that I like to remark first. Okay, so for this question, you see that we'll be able to have two ways to compute this one. However, at the end, you obtain the same answer. The thing that I want you to understand, and I like to practice with you a little bit, will be how could we integrate the double integral correctly? So for Calc 1, okay, so for calculus 1, when we like to integrate e to the 2x dx, okay, so when we like to integrate e to the 2x dx, the thing that we're gonna do is gonna be we're gonna do the substitution u equal to 2x, and then you just change the variable or do the integration by substitution. So for this one, we can just memorize the formula. It's gonna be e to the 2x over 2 plus c. Okay, so that's gonna be calculus 1. And in also calculus 1, when you like to integrate sine kx dx, so integrate sine is negative cos, so it's going to be cos kx over k plus c. So this one is just the integration by substitution, and you just have k is a constant. However, for calculus 2, okay, so for calc 2, the question turned out to be a little bit different. For example, if you like to integrate yx dx, okay, when you like to integrate yx dx, so the thing that you may feel uncomfortable turn out to be, hey, this one is variable or constant. The thing is, the thing that you need to ask yourself turn out to be, what are you doing? You like to integrate this guy with respect to x. This guy will become constant. Okay, so you can treat this number as number 2 that you have in calculus 1 before. Okay, so it's going to be like the first formula, but the constant turn out to be y instead. So this one is going to be just, if you understand, you're going to just answer this one. It's going to be e to the yx over y. It's like using the substitution with y is a constant. Okay, so it's going to be just the substitution, and it's going to be just y is a constant in this case. Okay, so this one is going to be the thing that you may have to like make yourself comfortable with this kind of computation that kind of feel different. Okay, let's do one more. If you like to integrate cos x squared y dy, if it turned out to be integrate cos of x squared y dy, you see that for this one, the constant turned out to be your x squared. Okay, so this one is your x squared, and you're gonna integrate cos. You have sine the whole thing x squared y. Okay, and for this one, you basically use the substitution. Let me use substitution for you a little bit. So for this one, I should let u to be x squared y. Okay, and you need to find du. Du is going to be d of x squared y, and you have x squared is a constant, so it's going to be x squared dy. Okay, so you have du dy equal to x squared. This is what you normally get, and you solve for dy like we did for calc 1, so it's going to be du over x squared. Okay, so it's going to be du over x squared. So for this one, it's going to be integrate cos, okay, u, yeah, so it's going to be cos u, and you have dy turn out to be du over x squared. Okay, so that my dy. So I did step by step like we do the first time for the substitution with each other. Okay, so this is what I usually highlight, right? So for this one, you see that don't be afraid about x squared. This guy is gonna be just constant, but a fancy one. Okay, so this one is going to be just constant, and you basically integrate cos, so it's going to be sine u over x squared. Okay, and you're gonna have this one is gonna be sine of x squared y over x squared plus 6. Okay, so for this one, it's going to be the thing that you have to be able to do. Okay, so that's going to be the integration by substitution that a little bit confusing at first. It's like you do the partial derivative that you may have to keep in mind which variable turn out to be constant and which variable turn out to be the thing that we are working with, or we like to differentiate it, or we like to, in this case, integrate it. Okay, so that is going to be the thing that we gonna do. Don't worry much. After first 2 lectures, you should be fine for this one. That one is not going to be that difficult. And the thing that you're going to have is going to be just the integration by substitution. It's no technique, no by part, no trick sum. Okay, so it's going to be just the basic integral by just the substitution. The next thing I like to teach you is going to be about the interpretation for the volume. You see that I give you the surface z equal to 16 minus x squared minus 2y squared. So this one gives you this surface. And we have the rectangular region D, okay, from 0 to 2, and it's going to be from 0 to 2 on x-axis and on y-axis as well. So you have x lie between 0 to 2 and y lies between 0 to 2. And the question asks you to find the volume of the solid above the xy plane under the surface, this one. So this one, I told you before that this one is going to be the double integral over the region D of your surface fxy dA. And this one can be written in two ways. So it's going to be the double integral from 0 to 2, 0 to 2 of your surface, which is 16 minus x squared minus 2y squared. Okay, so you have this one and you have dx dy. So for this one, let me choose. So for this one, this guy can be transformed into this integral. And I told you before that, okay, I told you before that when you like to integrate this one, you don't need to do both. Let me highlight the color for you. This one is the second question. So you see that the color must be correspond. Okay, so it's going to be the green one from for y and the purple one for x in this picture. And the thing that I like you to write down, another one can be just you can switch or you can interchange the order for this one a little bit to y squared dy dx. However, the boundary for this one is coincident to be exactly the same, 0 to 2. So for this one, I can have the green inside, the purple outside. Okay, so it's gonna be like that. Okay, and then, okay, and then you gonna have to pick one to integrate. You don't need to integrate both. Okay, so you don't need to integrate both. And some of you like used to ask me that, hey, can you show me where is our D a little bit? Your D here turn out to be your 0, turn out to be here, and your D turn out to be this one for X. Okay, so this one for X. And I need to draw on my own. So this one is for X and this one is for my Y. Sorry, that the red guy is for Y and the pink one is for my X. Okay, so it's going to be X between 0 to 2 and Y between 0 to 2 as well, that you can see from this picture. Another thing that I have to teach you will be how would we integrate something like this? How would we integrate something like this? If I want to integrate 16 minus x squared minus 2y squared dx. Okay, so if I want to integrate the purple one like this one, how could I integrate? So you see that you just do the thing that you did in calculus one. So you'll be able to just integrate term by term. So it's going to be 16 dx, x squared dx, and 2y squared dx. Okay, so this one is going to be integrate to y squared dx. Okay, and this allows you to just have 16x. Okay, because constant multiple. And for this one, integrate x squared dx, so it's going to be x to the third over 3. And for the final one, so you have 2y squared dx. So this guy is another fancy constant. Okay, so this guy is another fancy constant. So I have minus 2y squared times x. Okay, so for this one, and this one will be your integral. Okay, so that is gonna be it. Yeah, that's gonna be. Okay, so for this one, I'm gonna just pick one to compute for value, and the thing that I'm gonna pick turn out to be the first one. Okay, so let me copy this guy down. Copy. Okay, so I have this one. So I'm gonna begin by integrating this inside. Okay, so I'm going to begin by integrating this inside. So for this one, I'm gonna integrate 16 with respect to x. So I'm gonna have 16x, okay, like I have up here. I'm gonna copy them down. So it's gonna be 16x minus x to the third over 3 minus 2y squared x, okay? And you're gonna have x equal to 0 to x equal to 2. I did put x and y. I did put x equal to 0 and x equal to 2 in order to like warn myself a little bit that we are working with variable x, and the place that we gonna put my x is gonna be the x here, okay, that I have 3 places. So you would just have 16 times 2, 2 to the third over 3, and you have 2y squared times 2. And for this one, it's going to be for x equal to 2, and you're going to subtract by x equal to 0. Okay, so this one is for x equal to 0, and you integrate from 0 to 2, which is the outside integral dy. So this one is the green color. Okay, so that is gonna be your copy down the outside one. Okay, so look like this, and then you know that this guy already equal to 0, so it disappear. So for this one, you have integral from 0 to 2, and you have 16 times 2, so it's going to be 32, and you have 8 over 3, okay, and you have 4y squared dy, okay, and you're gonna just integrate 32y 8 over 3 y 4 third y to the third. Okay, so it's going to be 4y to the third over 3 from 0 to 2. So for this one, it's going to be 32 times 2, 8 over 3 times 2, 4 over 3 to the third. Okay, and this one is when y equal to 0, and you subtract, sorry, when y equal to 2, and then you subtract y equal to 0, which turn out to give you just 0, and you just calculate this number. So for this one would be 64 minus 16 over 3. Let me erase this 3 out. Okay, so you're not gonna confuse, and you're gonna have 8, right? So it's gonna be 32 over 3. Okay, and you see that the total turned out to be 64 minus 48 over 3, which is equal to 16, and this guy turned out to be, so this one is equal to 16. Okay, and it's gonna be 48. Okay, so it's gonna be 48. So this volume of the the volume of the, what is called, the solid. Okay, so the volume of the solid turned out to be equal to 48. So you see that if you compute the volume by computing the volume of the bar by using the Riemann sum, if you have 16 bar, so you have m equal to n equal to 4, you have 16 bar, and you sum the volume, you get 41.5. If you have 64 bar, so this one is a little bit finer. So you have m equal to 8, n equal to 8. You have 64 bar. The volume is equal to 44.875. And if you subdivide this one into 256 bar, m equal to 16 and n equal to 16, you're gonna get 46 minus for 46.46875. However, the exact volume, okay, so the exact volume turned out to be given by 48, and the way that we compute this one is gonna be you just compute the double integral for the value. So this one is gonna be the exact volume in this case. Okay, so this one is how we use the double integral in order to find the volume of the solid bounded above by the surface z equal to fxy over the rectangle region. Okay, so this one is going to be just the first introduction for this guy. Okay, I gonna stop here first. I'm gonna do another clip for more example on this double integral, and I'm gonna teach you how to evaluate for value next.